In this lecture, we'll learn about making models robust to adversaries. You've probably seen adversarial examples before. It starts with a clean image, and it's added to some small amount of noise, and the resulting image is fairly similar to the original image, except that it's subtly different and causes the classifier to make a mistake. It causes it to say that the cat image is actually something that it's clearly not, like guacamole. The adversarial distortion, by the way, is carefully crafted. It's not random noise. This picture is accurate for undefended off-the-shelf models, but today's models actually are fairly robust to adversarial distortions that are that small. Models can now be defended against imperceptible distortions. In contrast, modern adversarial examples have perceptible changes. Let's look at some examples. There's X and XAdv. XAdv is the adversarial example. So with the red truck, we can see that there are some changes to the image, and likewise for the coffee maker. There are perceptible changes. The shadows changed, for instance, and on the coffee maker, there are markings. Here, the adversary made changes to the images that are perceptible, but the category is unchanged. Consequently, the adversary still was able to cause the model to make a mistake, and that's a problem for safety. Adversarial examples is not about imperceptible distortions. It's about adversaries changing inputs and causing models to make mistakes. Modern models can be made robust to imperceptible distortions, but they are still not robust to perceptible distortions. There are other motivations for researching adversarial robustness. One motivation is optimization pressure. In the future, artificial agents may optimize and may be guided by neural network proxies, such as networks that model human values. These proxies instantiated by neural networks, that is, networks that assign scores to agent actions, will need to be robust to optimizing agents. So the basic picture is there's an agent and it's taking actions to try to get a high score according to a neural network that's representing something like human values. So if an agent is acting in keeping with human values, it would be assigned a higher score. And if it's doing something undesirable according to human values, then it might be given a lower score. Agents are somewhat optimizing against this neural network proxy for human values. And if this proxy isn't robust, then agents may be guided in a wrong direction. And so the agents wouldn't pursue what we would want. Similarly, models that can detect undesirable adversarial agent behavior will need to be adversarially robust. Otherwise, those AI agents could bypass these detectors. So this is another reason for wanting adversarial robustness. Before jumping into some of the technical expressions and formulas involved with adversarial robustness, let's have a brief refresher about what an LP norm is. The L1 norm is the sum of the absolute values of the dimensions of a vector. The L2 norm of a vector is the sum of the squares of the dimensions of the vector, and then you take the root of that. The L infinity norm is the maximum of the absolute values of the dimensions of the vector. Before talking about deep networks, let's just talk about trying to come up with an adversarial example for a simple binary classifier. Say our binary classifier is as follows. There's a weight vector and an input vector. At the right, we visualize a one-dimensional version of this. Say that the input vector is x, as specified as follows, and the weights are specified by this table as well. Currently, the sigmoid's value is approximately 5%. But we could come up with an adversarial example that perturbs each input dimension by a small amount. If we make 2 become 1.5, and -1 become -1.5, and 3 become 0.5, etc., then we can change the sigmoid's value from 5% to 88%. In this case, the L infinity norm is just 0.5. So we did many small changes, but we were able to change the probability value from a small amount to a fairly large amount. Here's some lessons from this example. One is that the cumulative effect of many small changes can make the adversary powerful enough to change the classification decision. And adversarial examples exist for non-deep learning simple models. So it's not the case that deep networks are so complicated and that's why they have adversarial examples. It's actually a more fundamental property of many machine learning systems. Now let's describe a simple toy adversarial threat model. This threat model assumes that an adversary has an LP attack distortion budget subject to some constraint. So assuming a fixed P and epsilon, the adversarial example must not differ from the original example by more than epsilon. So the difference between the adversarial example and X must be less than epsilon. Now, not all distortions necessarily have a small LP norm. For example, a small rotation may actually have a very large LP norm. But this simplistic threat model is common since it's a more tractable subproblem. Also, the adversary's goal is to find a distortion that maximizes the loss subject to its budget. So the adversarial example is equal to X plus the argmax of the loss. It's trying to come up with It's trying to come up with a distortion delta such that when added to the example, the loss is largest. So argmax returns the delta that maximizes the loss. Let's speak about a simple adversarial attack that conforms to the LP threat model. The FGSM attack is a simple attack. It's as follows. X sub FGSM is equal to the original image X plus epsilon times the sign of the gradient of the loss. This is different from X plus epsilon times the gradient of the loss, which we'll see why in just a second. FGSM performs a single step of something like gradient descent to increase the loss, and it obeys an L-infinity attack budget. It uses up the entire L-infinity attack budget, and the difference between X of FGSM and X is equal to epsilon. Why don't we just use the gradient of the loss? Why do we take the sign of the gradient of the loss? Well, that's so that in each dimension, it moves epsilon away from the original input. Meanwhile, if we did the gradient of the loss, potentially some of the dimensions would be greater than epsilon, and many of the other dimensions would be less than epsilon. The sign snaps it so that it's 0 and 1, and then when multiplied by epsilon, the perturbation is either epsilon or negative epsilon. So it completely uses up the attack budget and keeps it well within, or keeps it subject to, the L-infinity constraint. This attack is called fast because it uses a single step. But right now, this isn't really a strong attack anymore. It's actually fairly easy to defend against with modern methods. However, off-the-shelf models can definitely be vulnerable to the FGSM attack. Let's speak about an attack that is stronger than the FGSM attack. Unlike the single-step FGSM attack, the PGD attack uses multiple gradient descent steps and so is more powerful. The pseudocode for this attack using an L-infinity budget is as follows. I'll note that I'll be showing the L-infinity attack version, but the L2 attack is fairly similar. The first step is to randomly perturb the input by some noise. So the adversarial example at the first step is actually just X plus some random noise. This random noise is uniformly sampled from a uniform distribution between negative epsilon and epsilon. We do this because, for more diverse examples, we want to randomly initialize the optimization process. Then, for multiple steps, we'll update the adversarial example with the following expression. We'll define what P is later, but we do X plus alpha times the sign of the loss of the, or alpha times the sign of the gradient of the loss. We do this for potentially 7 steps, as would be the case for CFAR10. So looks fairly similar to FGSM, and this script P is defined as a clipping operation. It's done element-wise to the input. So if the input is epsilon away from the more than epsilon away from the original example, then it gets clicked. This keeps it subject to the L-infinity budget. How do we make models more robust to these sorts of adversarial examples? The best known way is currently called adversarial training. The procedure is usually something as follows. First, you sample a mini batch from the dataset, and then you create adversarial examples, x of ad, from the mini batch example x. For adversarial training to be successful, you often want the adversarial example constructed through a multi-step attack such as PGD. If one trains against FGSM type of examples, that usually won't be sufficient for defending it. Then, with the adversarial examples, you optimize the loss. You train the network to correctly classify the adversarial examples. That's basically it. And adversarial training can improve robustness to those sorts of adversarial examples, but it comes at the cost of reducing the clean accuracy on adversarial examples by a substantial amount. And it doesn't completely defend against those sorts of adversarial examples either. Adversarial attacks and adversarial training can come in some different flavors. There's untargeted attacks and targeted attacks. An untargeted attack maximizes the loss, whereas a targeted attack optimizes examples to be classified as a predetermined target y tilde. So untargeted attacks for adversarial training are standard for CFAR, but targeted attacks for adversarial training are standard for ImageNet, since ImageNet has many similar classes. Let's look at an example. Here's the original image, which is a golden retriever. If we do untargeted adversarial attacks, the adversary is going to try and maximize the loss and make it classified as something different. Since ImageNet has so many different classes, the model may have a Labrador Retriever be the adversarial example. So it's not making it think it's an egregious class. The adversary is making it think it's a fairly similar class. Meanwhile, a targeted adversary will randomly sample a class, such as great white shark, and then it will construct the adversarial example to confuse the model to think that the golden retriever is actually a great white shark. So on ImageNet, if we trained against an untargeted attack, the model would use its capacity to avoid subtle mistakes, but it wouldn't necessarily be defended against egregious mistakes. Also, targeted classes are randomly sampled from the set of all classes, excluding the correct class. This ensures a high probability that adversarial examples are not just subtly wrong, because the probability a targeted class would be similar to the true class is small when sampling over all classes. Assessing and estimating the robustness of a model against adversarial attacks can be very subtle. Let's look at a historical example to see how this is so. Szegedy et al. In 2014 discovered adversarial examples, and a year later, some defenses were proposed. A variant of adversarial training said that they solved adversarial examples, and Papernaw's paper on defensive distillation also gave that impression. But somewhat thereafter, defenses were subverted by new attacks. This interplay between attack and defense with this cat and mouse game continued for many more papers, and in 2017, Carleni and Wagner wrote a paper where they bypassed 10 defenses in the same paper. This shows that there were many defenses proposed, and many of them didn't ultimately hold up. Consequently, researchers can get adversarial evaluation wrong. To prevent this from happening, there's a non-exhaustive checklist for having more proper and sound evaluation. For example, they propose that researchers test their model against adaptive attacks, non-differentiable attacks, or test against a broader threat model. There are libraries that help automate some of this, such as AutoAttack, but still, adversarial evaluation is very subtle, and all people researching in the area need to be aware of the various pitfalls when trying to construct an adversarial defense. There are different ways of evaluating and testing the robustness of models. There's a white box way and a black box way. When adversaries don't have access to the model parameters, the network is considered a black box, and only model outputs are observed. However, many researchers prefer white box evaluation, because if we rely on black box assumptions, this can be likened to security through obscurity, which is generally thought to be a fragile strategy. So the difference between black box is that the internals are not known, and you're testing as a user. And with a white box situation, the internals are fully known, and you're testing as a developer. Another way to attack models would be through transferability attacks, which can even affect black box models. The basic idea behind transfer attacks is that an adversarial example crafted for one model can be used to attack many different models. So in this way, adversarial examples made for one model could potentially transfer to several others. More specifically, if we have two models, say M1 and M2, and if X sub adv is created for the first model M1, then it could create a high loss in the second model. It could cause the second model to make a mistake. And this is true even if M2 is a completely different architecture or trained differently. Often, adversarial examples can transfer to different models. Now, I should note that the transfer rates can vary quite a bit, so this isn't a highly reliable attack. That said, transferability demonstrates that adversarial failure modes are somewhat shared or consistent across models of different architectures or different weights. Therefore, an attacker does not always need to have access to a model's parameters or even its architectural information to attack that model. Let's look at a case study showing that adversarial examples can transfer and be robust even in more realistic situations. In the previous discussion, we were looking at adversarial examples made on computers, and they're being preserved and represented in precise digital formats. However, if one prints off an adversarial example on a printer, and if one takes a picture of it, that can still cause models to make mistakes. So they can withstand some instantiation noise or sensor noise. This points to their robustness, even though they're relying on very subtle small changes. So for instance, here we have a washer in the picture below, and when it's a clean image, the model gets the classification correct. However, when we add some adversarial noise, it incorrectly classifies it as a safe. And when we increase the adversarial noise, even though it's still fairly subtle to the human eye, the model thinks that it's a safe, and as the second most likely class, it thinks it's a loudspeaker. So this demonstrates that adversarial examples don't just rely on extremely precise small changes that break the moment there's a little bit of noise. They can be somewhat more robust to noise, including real-world noise. Faced with the power of all these adversarial attacks, what are some ways that we could improve the robustness against them beyond doing just typical adversarial training? Well, one possibility is to train on more labeled data, but there's only so much labeled data to go around. CFAR 10, for instance, only has 50,000 examples. But what this plot shows at the right is that as the training set size increases, there are improvements to adversarial robustness. So this suggests data is useful, but unfortunately, we're quite bottlenecked in the amount of labeled data. One possibility is to adversarially pre-train using adversarially distorted data for different tasks that have more labeled data. So, for example, let's say we wanted to increase CFAR 10 or CFAR 100 adversarial robustness. We could then first adversarially train a model on ImageNet, which is a larger labeled data set, and then adversarially fine-tune the model on CFAR 10 or CFAR 100. So if we perform normal training, as the table below shows, the adversarial robustness is, of course, 0%. And if we perform vanilla adversarial training, we get, in the case of CFAR 10, something about 46%. If we adversarially pre-train on ImageNet, and then adversarially fine-tune on CFAR 10, then we end up getting approximately 57%. So it's possible to leverage other larger labeled data sets, adversarially pre-train on them, and then fine-tune with adversarial training on the task that you care about. This also suggests that adversarial robustness is not just for one specific data set. When you're performing adversarial training, the model isn't just learning to respond to adversarial examples for the specific images that it sees in the training distribution. This suggests that adversarial training is actually endowing it with adversarial robustness to different adversarial examples more generally. Otherwise, it wouldn't be able to transfer. So this suggests models during adversarial training are not just doing something like memorization. They're actually learning some generalizable, more robust features which can transfer over to other data sets. This is one way to ameliorate the data bottleneck by adversarially pre-training on other related distributions. Data augmentation also can help improve adversarial robustness. So beyond using more data, we could also have models squeeze more out of their existing data using data augmentation. An example data augmentation techniques that works with adversarial training is cutmix. Here's the pseudocode of cutmix, and here's an example of cutmix juxtaposed with other data augmentation techniques such as mix-up and cutout. The basic idea behind cutmix is take a portion of an image and replace that portion with a different image. So create a rectangle in the image, cut it out, and then swap it with a different example. So in this case, there might be 30% of the image as a cat, and that would mean its label for this example should be 30% confidence of cat, 70% confidence dog. This simple data augmentation technique can help improve adversarial robustness. Let's look at the robustness conferred by various data augmentation techniques. As we can see, cutmix has the highest adversarial robustness of all the data augmentation techniques considered in this paper. It's, for example, doing better than mix-up and cutout that we saw on the previous slide. It's doing better than some other popular data augmentation techniques such as auto-augment and rand-augment too, which look like they actually harm the adversarial robustness. So it's not the claim that all data augment techniques do better. Some of them may end up harming the robustness. Cutmix is a Pareto improvement over the baseline. The baseline data augmentation technique is pad and crop. We can see that the adversarial robustness is higher and the clean test accuracy is higher. There's a caveat in using cutmix, which is that you need to use exponential moving averaging for the parameters while training. That is to say that when given the parameters, at each iteration, the model is updated with an exponential moving average modulated by a parameter tau. This is kind of like when doing momentum or atom. There's an exponential moving average to make sure that you don't over-update in a particular direction and so that you get a smoother estimate. This isn't necessary for doing typical data augmentation, but when doing data augmentation with adversarial training, exponential moving averaging is currently important. Smooth activation functions can improve adversarial robustness. This is in contrast to sharp activation functions such as ReLUs, because they can make adversarial training less effective. By improving the gradient quality for either the adversarial attacker or the network optimizer, smooth activations such as the GELU can improve adversarial training. So what we can see on the right is the ReLU is sharp because at around 0, there's a discontinuity in the derivative. That's not a smooth function. Meanwhile, the GELU is a much smoother function. This can turn out to be quite practically significant. If we are trying to adversarially train a ResNet 50 and we use the typical ReLUs, then we get an accuracy of about 26%. But if we adversarially train a ResNet with GELUs, then the adversarial robustness is about 35%. So we can have about a 9% boost just by swapping the activation function to be smoother. This result is mostly just observed empirically. There aren't decisive theoretical reasons for why this is so, as is the case for most things in deep learning. Let's turn to a broader threat model. We want models to be robust to unforeseen adversaries, not just adversaries with their attack specifications known beforehand. Attackers in the real world don't need to conform to a small LP adversarial perturbation budget. They could apply many different transformations to the image. They could apply ones that we've never seen before. So we would like models to be robust to unforeseen attacks. However, models are far less robust to attacks that they have not trained against. For example, if a model has adversarially trained against L-infinity adversarial attacks, against other L-infinity adversarial attacks, it gets 88%. However, If it's adversarially trained against L-infinity attacks, but then we're testing against something like adversarial snow, then it gets 37%. Now, what do I mean by adversarial snow? In this example, we can see what randomly initialized snow is. Let's imagine we've created an adversarial or a typical snow distortion through some computer graphics. That won't necessarily change the classification. It often does, but in this situation, it doesn't. Meanwhile, at the right, there's adversarially optimized snow. The snowflakes' intensity, location, and angle are adversarially optimized. And this adversarial example is successful at changing the classification. So it's possible to create lots of diverse adversarial attacks and even create adversarial snow through optimization. Now, to get a good estimate of robustness to unforeseen attacks, one possibility is to train the model on some specific attacks, and then during test time, show it many different attacks that have not been encountered before, and see its robustness against those. That gives some empirical estimate of how well it will generalize to new types of attacks, and how robust it will be in the face of them. That doesn't, of course, cover all possible unforeseen attacks, but it gives some estimate, and gives us some ability to see whether we're making progress on the problem. As we've seen, adversarial examples don't have an easy fix, which might lead one to wonder, what are some of the factors or causes that make adversaries as powerful as they are? Well, some factors are that they get their strength from their degrees of freedom and the extent to which they can modify each degree of freedom, which we might call their budget. So, for example, with adversarial noise, the attack strength depends on the number of pixels that can be attacked or modified, as well as the amount that each pixel can be modified. One would be the degrees of freedom, one would be the budget. So the degrees of freedom of an attacker might be reduced if you require that the pixels have some sort of correlation between them. That would reduce their effective degrees of freedom. For instance, adversarial snow would have fewer degrees of freedom than adversarial noise if we're trying to attack the entire image. That's because the attack in the case of snow needs to conform to a specific structure. That reduces the effective degrees of freedom. Another factor that affects the strength of adversaries would be whether we have adaptive models. Adaptive models can reduce the power of adversaries, since adversaries are required to keep changing their attacks to successfully subvert an adaptive model. So we present here 3 different factors that influence an adversary's strength: the adversary's degrees of freedom, the adversary's budget, and whether the defender is adaptive. Another factor that influences the strength of an adversary is whether the input space is discrete or continuous. The continuous attacks mean better gradients, so they tend to be more powerful. But it's possible to construct adversarial attacks for NLP models, even though they have discrete inputs. For example, it's possible to create a typo attack. By creating a typo, it's possible to flip the classification. Another attack would be to add distractor text, which can also flip the classification. Some popular attacks include text bugger, which induces typos. This compositional attack makes use of composition. BERT attack makes use of context. BERT attack uses pre-trained BERT models to perform mass language model prediction to generate contextualized potential word replacements, so as to replace some of the crucial words and cause the model to make a mistake. So it's not just randomly flipping words, it's using its contextualized understanding of how the model tends to process these to create a more powerful automatic attack. We've mostly focused on continuous attacks because they tend to mean stronger attacks, and that might be more representative of future long-term concerns when optimizers are more powerful. But it still can be useful to look at text-based attacks too. Even though the attacks tend to be somewhat weaker, many of the interesting deep learning phenomena certainly is going on in natural language processing, so it's important to look at that as well. In closing, let's look at the important topic of robustness guarantees. One might wonder, how can we have confidence in a model's behavior during test time? Are all bets off when models are deployed? Well, fortunately, it's the case that we can prove properties about how a model will behave when it's deployed. So some might think that the test set doesn't have enough to find the important faults in a model, and so consequently, empirical evidence is insufficient for having high trust or confidence in models, but it's possible to have provable guarantees or certificates for how a model behaves given just the model weights. One line of robustness guarantees research studies classifiers whose prediction at any example X is verifiably constant within some set around X. So in the figure at the right, if we have a new example seen during test time, we can prove that it will behave correctly on that example and in the set of examples around that example. Consequently, there's a sort of certified radius, so we can have some guarantees about how models will behave. These guarantees are demonstrated using mathematical properties of neural networks, so consequently, this is a research area where people with a theoretical background can make a difference.